Just wanted to give you a little video kind of giving you some intuition for the fundamental theorem of calculus part 1. So I'm going to go over a general intuition for it and kind of define accumulation function, something that we talked about before we left a little bit. And then I'll do a couple examples. This is just as a supplement to your Khan Academy content. So we call a function that looks like this an accumulation function. And the thing I want you to note about this is g is a function of x. And so our variable x is actually the upper limit of this integral, where the lower limit represents some constant. And so the way we've been thinking about integrals are just areas under a curve, right? So if this blue curve is f of t, then this is called an accumulation function because as we increase x, right, that's going to represent an increasing area under the curve f from a to whatever value we let x be. Okay? So let me show you this in an example. And this is going to kind of set up the fundamental theorem of calculus. So here, I've defined my function g of x as an accumulation function, the integral from 0 to x of f of t dt. All right. And I'm going to find a few values of g. So first I'm going to find g of 0. So g of 0 then is just the integral from 0 to 0 of f of t dt. And so there was a property we know about definite integrals that when the upper and lower limits of integration are the same, that's an area of 0. That would be like the area under a single point which has no width. So that's 0. So I know g of 0 is 0. All right, so then g of 1. So now we're looking at the integral from 0 to 1 of f of t dt. We're just going to interpret this geometrically. So what we have there is an area under the curve in this little triangle, right? And so we can just use geometry to find that. So we know the area of a triangle is just 1/2 base times height. So that's 1/2 1 times 2, which is 1. So I know that g of 1 is 1. We're just going to continue this process for the next couple points. So let's see, what did I want us to find? G of 2, 3, 4, and 5. All right, so g of 2 is the integral from 0 to 2 f of t dt. So that's the area under the curve between 0 and 2. So it's going to be our triangle, which had an area of 1, plus the area of that rectangle I just shaded in. Area of a rectangle is just base times height, so 1 times 2 is 2. There we go, that gives me 3. So you can see how the area is accumulating as I increase x. So then g of 3 is the integral from 0 to 3. Oops, that's 3. So it's going to be that 3 plus an additional area. So this one we're going to have to kind of estimate. We can't actually do the geometry, but that's okay. We're just going to estimate it. So that looks like an additional about 1, I'm going to say it's 1.5 boxes. So plus 1.5, so that's going to be 4.5. All right, g of 4, integral from 0 to 4 f of t dt. It's going to be that 4.5 that we've already accumulated plus whatever it takes to get to 4. Now, one thing I do want you to notice is that in this case, the curve now dips below the x-axis, meaning remember that if the area is below the x-axis, we need to interpret it as negative area. So that's about the same area as the area was up here, but we're going to now interpret that, as negative. So I'm going to say 4.5 minus 1.5, which is going to get us back to, back to 3, right? So g of 4 is 3, and then g of 5 is the integral from 0 to 5 of f of t dt, and that's going to be that 3 plus the additional area to get to 5. Now, again, we're under the x-axis, so this is all negative area. I'm going to say that looks symmetric to the area we just shaded in, so I'm going to say that's an additional negative 1.5, which is going to get us to 1.5. All right, great. Well, now we can sketch a rough graph of G, because basically I have 6 coordinates that I can sketch. G of 0, G of 1, G of 2, G of 3, G of 4, and G of 5. So I'm going to plot those. I'm just going to do it on this same coordinate axis. Let me erase this stuff so it's not distracting us. But I'll plot G in red. So G of 0 is 0, so I have the point 0, 0. G of 1 is 1, so I have the point 1, 1. G of 2 is 3, so 2, 3. G of 3 is 4.5, so we're going to be a little bit off the axis, but let's say 4.5 is about there. G of 4 is back to 3, and G of 5 is 1.5. Whoops. Right about there. So you can imagine we found these discrete points, but g of x is going to be a continuous function, and it's going to look something like that. All right. So there's a better drawing than mine. All right, so now let's get to the fundamental theorem of calculus. So I'm going to start with this little diagram, and I'm going to define a function g. This is an accumulation function, so g represents, remember, the area under the curve of f between a and some value x. And what I want you to do is focus on this little rectangle, and I want to find the area of this rectangle. And so we could say that one way to do it is just base times height. Now, the way that they've set up these notations, the height of the rectangle is f of x. The base of the rectangle is h, okay? So one way to define that rectangle is this way. We can say that the area of that rectangle is just, is just f of x times h. But another way I can do it is using my little accumulation function. So I want to think about how I would define that rectangle using the accumulation function. And I accidentally erased it, so let me rewrite it. G of x is the integral from a to x of f of t dt. So right now, if my x is where it's labeled, then that g of x just represents all of this area up to x, right? Well, I just want the area under the curve in that rectangle. So another way, what if I looked at g of x plus h? So g of x plus h, well, if you think about that, g of x plus h is just the integral from a to, instead of x, we replace x with x plus h of f of t dt, right? So if you think about that, that would be this total area here. So all the way from a under the curve, not stopping at x, but yes, stopping at x plus h. But again, I just want the area inside the rectangle. I don't want all of that area. So what I'm going to do is then subtract off g of x, okay? So subtracting off g of x is just going to have the effect of erasing everything to the left of x under the curve, right? So just like that, and leaving me with what I want. And so I'm going to say that f of x times h is approximately equal to that, because in actuality, when I use the accumulation function, remember, I'm finding the exact area under the curve, whereas the f of x times h is the area of that whole rectangle. But I'm now going to kind of manipulate this approximate equation. I'm going to divide both sides by h.
What did you think, Dad? Yes,
Hold on. All right. Sorry about that. So once we divide out the h, we actually end up with this, which is to say that f of x is approximately equal to g of x plus h minus g of x over h. Well, how can we get rid of the approximately equal to and make it exactly equal to? Well, the thinner the rectangle, the more closely the area of the rectangle will approximate the area under the curve. So they'll be exactly equal if I let h go to 0. And then what we have is something that hopefully looks familiar. I know it's been a while, but if you look on this side of the equation, this is the definition of derivative. Specifically, it's the derivative of g. So this equals g prime. And so what we did was just make an extremely important connection between f and g, namely that f of x is the derivative of g of x. So what we've just established is that a derivative is the inverse to an integral. A derivative effectively undoes an integral, since g prime of x equals f of x. So we've established this dual relationship that we've been mentioning for quite some time, right? So if g is the integral of f, then g prime equals f. Therefore, derivatives and integrals are inverse operations. And that is the fundamental theorem of calculus part 1. It just establishes that if g is the integral from a to x of f of t dt, and f is a continuous function on a closed interval, then g prime equals f. So super important result. Okay, so let's get to some quick examples of how we use that result. One thing to note is the specific way your function must be set up for this to be the case, right? Your lower limit has to be some constant. It can be any constant. Your upper limit is your variable, x. If that's the case, then g prime is just going to equal f of x. In this case, my lower limit is 0. That's a constant. My upper limit is x. And my function, let's think of that, let's call that f of t, right? So f of t is root 1 plus t squared. So then fundamental theorem of calculus just says that g prime of x should equal f of x, meaning g prime of x is my function, but in terms of x, not in terms of t, so all I'm going to do is replace my t's with x's, so g prime of x is just root 1 plus x squared, and I'm done. So taking the derivative effectively just undoes the integral and leaves us with the integrand in terms of our input variable x. Okay, so this one's a little more challenging. Give me 1 second. Oh, I just realized I did not full screen it. All right, so I have a very particular way of thinking about a problem like this that I feel like hopefully simplifies the process, and it may be slightly different than the way they do it on Khan Academy or something like that. So first, let's look at our integral. Our integral is a function of x, right? So I'm just going to define it the way we've been defining it. So if we define it in terms of g, and I say, okay, so g of x equals the integral from 1 to x to the 4th of secant t dt. What's really important to understand here is g is just some function of x, so it's this kind of weird looking accumulation function, but it's still just some function of x. So let's give it a generic name instead. So let's call it h, right? Well, h is, in this case, we're not just plugging in x, we're plugging in x to the 4th. So really what we have is that g of x equals h of x to the 4th, because that's our input. And then what they're asking us to do is take the derivative, right? Well, what rule would you have to use to take the derivative when you have a function plugged into a function? Chain rule, right? And chain rule dictates that we take the derivative of the outside function, so h prime of x, leave the inside function alone, and then multiply by the derivative of the inside function, which would be 4x to the 3rd in this case. Now in this case, our outside function is our accumulation function. So the derivative of that just undoes the integral and leaves us with our integrand, but with our new input plugged in, right? So our new input in the case before this was just x, but in this case is x to the 4th. Good, so what we really are going to end up with is secant of x to the 4th times 4x cubed. So when your upper limit is something other than just x, you have to use chain rule. And you just use chain rule the same way we've used it before, the derivative of the outermost part of the function. So taking the derivative of the integral undoes the integral and leaves our input where t was, times the derivative of the inside function, so times 4x to the 3rd. So this is my final answer. The derivative of that accumulation function is secant x to the 4th times 4x cubed.